Fortuna Major. Here, listen. She just won't let me in.
Fortuna Major.
No, wait. What's this? Amazing! Just with my voice.
So chances are you've probably seen something like this happen in movies and TV shows before, and it's usually just added in for comedic effect, but this year in Physics 20 I learned that it is possible and how it's possible, so let's get into that. So what makes events like this,
In a 40-mile-an-hour gale, the center span weaves like
this,
Mom, I broke it! You did not.
and even things like this possible? It's all because of a little thing called resonance. So let's get into the basics. Resonance is defined by the Merriam-Webster dictionary as being a vibration of large amplitude in a mechanical or electrical system caused by a relatively small periodic stimulus of the same or nearly the same period as the natural vibrating period of the system. So let's break this down a little bit. Imagine you're swinging on a swing. Assuming no air resistance, the swing's motion could be graphed as a sine function, just like this one. Realistically speaking, this example would include air resistance though. Air resistance would make the graph look more like this. Notice how the period stays the same, but the amplitude changes with each wavelength. But this isn't very fun because eventually the swing would come to a stop. Maybe you'd like someone to push you. Notice how the frequency of the swing is the same as the frequency of the person pushing the swing. The person's pushes are matching the natural resonant frequency of the swing. These two mechanical systems working in sync will cause them to increase in amplitude. The closer the person's pushes are to the natural frequency will create more resonance, but it doesn't have to be identical. Okay, so these three graphs represent how waves interact with each other. So as we can see from looking at graph A, it's going to have the greatest increase in amplitude. When there's overlap, amplitude increases. A better way to visualize this is this graph. So the green here represents the overlap, which is also going to represent the amount of resonance between the two wavelengths. So this one we can tell that they're at two different frequencies and there's very little overlap. So this next graph shows two waves that have the same period but different amplitude. So we can notice that there's a little bit more resonance between them. So the last graph here shows what two waves would look like if they had the same frequency, all the same characteristics, and they were interacting with each other. So this might be an example of a graph that would be represented by being pushed on a swing. So now that we know a little bit more about how resonance works, how does it work when it comes to a wine glass and an opera singer? Every object has a natural frequency that it oscillates at. The formula for determining natural frequency looks a little bit like this, but we don't need to know all that, thankfully. So all we need to know is that frequency equals 1 over period. So this here is my wine glass that I decided to use. Took a couple tries, but this is how I determined the natural resonant frequency of the glass. I tried my best to match it, but I'm not a very good singer, so I then tried some frequency makers off of YouTube, but that didn't work either. So I expected the glass to at least vibrate a little bit, but it did not. So I think here are my reasons for failure. Number 1, my experiment was just too quiet. Amplitudes of the wavelengths must be very large for resonance to occur. Number 2, imperfections. Imperfections in the glass may cause some dampening to occur. The glass also might have been too thick for resonance to be observable. And 3, the frequency might not have been accurate enough. It's hard to determine the natural resonant frequency through listening alone. However, in a perfect environment, we would be able to observe the glass oscillating. If there were any cracks or weak areas, resonance could cause the glass to break. So thank you for watching. I hope you enjoyed this video. I hope you learned a little bit about resonance and how physics is just so cool.